Good evening. You hear me?
Yes, sir.
Yes, sir.
Thank you. So what we'll do is we'll start with week 10. So week 10 is continuing with constraint optimization with the inequality constraints, right? So that's the main part that we are going to look at today. So we left at this study of convex functions. So that is where we left, right? So let's first quickly revise that definition. So a function f from some convex set, right? So some convex set S to R. So first of all, you have to, this is important, right? So S is a convex subset. So let S be a convex subset of Rn, right? That's where you are. So a function f from S to R is said to be convex if for any x1, x2 in S and any lambda in this range, the following inequality is satisfied, right? So f of lambda x1 plus 1 minus lambda x2, this should be less than or equal to lambda f of x1 plus 1 minus lambda f of x2, right? So that's the whole idea, right? So this is the definition of convexity. So this we are already familiar with, right? So bowl shape functions are what are convex functions. Now what we are going to do today is we'll start with properties of convex functions, and then we will see the list of properties, and then we'll move on to inequality constraints. Okay. So the properties are quite a few. These functions are very well behaved. So what we'll assume is f is convex from some S to R. So I will not go over the proofs. The proofs I have what I have done is I have graded them out so that you can refer to them later, right? When I upload the document, so that there is some sort of completeness. Okay, maybe a couple of proofs here and there I will go over it, but otherwise you can just focus on the text in bold. Okay, bold meaning which is not grayed out. Okay, so the first property is if f is convex, then any positive multiple of f is also convex, right? So for example, maybe below everything I can give some examples. So for example, say f from R to R, f of x equal to x square is convex, then f of x equal to 7x square is also convex, right? So this is like a direct application of this property. So another example could be if you have let's say something like f of x comma y, right? So this is x square plus y square. This is convex. Okay. So why is this convex? F of x equal to x square plus y square. Why do you say, or how can we say that this is convex?
It is sum of two convex functions.
Okay. But this is like a different, the domain itself is different, right? So this is in R2. So what other condition will you use to show that it is convex? So one thing that you can use is the Hessian, right? So the Hessian will be what for this? H second derivatives will be 2, 0, 0, right? Okay. So this is like the Hessian for this function at any point. And since this is positive definite, right? So therefore, f is convex, right? So you start with that, and then same thing here also, right? So f double prime is 2, which is greater than 0. Therefore, this is convex, right? Now, then using this property, what can you say? F of x comma y equal to say some 10x square, 10 times x square plus y square is also convex. Okay, so that is a very simple property. Now, I hope it is clear, right? So this property, I hope it is clear. So next one is that the sum of convex functions they are also convex, right? So this is if f and g are convex, then f plus g is convex. The proof is very, very simple. So you just use the definition of convexity and you add the two inequalities. So this will generate two inequalities. You just have to add them, right? So quickly we'll look at a couple of examples. So for example, f of x equal to x square. Can you tell me some other single variable convex function? What other convex function are you aware of? Any example? Is sin x convex?
No, sir.
Okay, no. So what else can you think of? E power x, right? So that's a very useful example to have. So e power x is another convex function. So you can therefore say that. So h of x equal to x square plus e power x is convex, right? So yeah, linear functions are convex. The only problem with not problem, but the only thing about linear functions is that they are both convex and concave, but they are still convex. So I mean, you can still say that they're convex functions. So linear functions, yeah, they are convex, but you should also remember that they are also concave. Okay, so that is x square plus e power x, for example, is convex. We can maybe plot this and see how it looks. So this is x square plus e power x, right? It kind of looks more or less like x square. So maybe you should try something like x square minus log x, right? So negative log x is also convex, right? So that is convex, x square is convex. You can see that this is still a bowl, okay? So maybe I'll add, this is one example. So another example would be x square f of x equal to x square and g of x equal to negative log of x, right? Log to the base c, base 10 doesn't matter. Their sum is convex, right? So what is this? This is f of this h of x equal to x square plus x square minus log x, right? So that is this function. So this is also convex, right? So what else can you think of? If f of x is convex, if f and g are convex, then what can you say about say 3f plus 7g? Is this convex?
Yes.
How do you
Yes.
know that? Why is this the case?
Using the above two properties.
Correct. Using the above two properties, right? So this is scaling by a positive quantity, so that is convex. This is another convex function, and then sum of two convex functions, right? So convex. In fact, what you can say is that if so you can say this, if f1 dot 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 till fn are n convex functions, then can you complete it? What do you think I'm going to say?
Linear combination of those functions where each parameter is greater than 0.
Correct. Yeah, very good. So any linear combination of these convex, any positive linear combination, right? So any positive, okay, no, maybe that doesn't sound correct. Any linear combination of these convex functions where the coefficients are positive is also convex. Okay, so that is what we mean mathematically. It's like some alpha 1 f1 plus alpha 2 f2 plus alpha n fn is convex whenever alpha I is greater than 0, right? So of course you could have alpha I equal to 0, but then that's trivial, right? So that is just like getting rid of some function. So that's not very interesting. So we don't have that. Yeah, yes, Pradeep, you have a question?
Sir, can we say that negative of convex function is always concave?
Yeah, that is the definition of concave function, right? So negative of a convex function is a concave function. Yeah. Okay, so that is the second property or third property or second property, right? So that is that. And so next property is that if the composition of functions, when is it convex, right? So if you have f of x and g of x, when is f of g of x convex? Here there is, as you would have seen in the lectures, those who have seen the lectures, you have to be careful. So f is convex, g is convex, that is a requirement, but that is not enough, right? So f has to be some increasing or not. So non-decreasing means what? Something that is that never goes down. Okay, so it's like an increasing function, but then it could be constant for some range as well. Okay, that is a non-decreasing function. So f of g is convex, right? So example functions could be what? For example, f of x equal to what is an increasing or a non-decreasing convex function?
E
That we
power
can
x.
e power x is a non-decreasing convex function. In fact, it is strictly increasing. And g of x can be any convex function, right? So g of x can be x square or whatever, right? So then h of x equal to f of g of x, right? So this is what
X square.
e power x square is convex, right? So this is convex. Now notice that you can get really complex functions once you start, composing two functions. Okay, so that is. So does anyone remember the counter example that Sar said? So where f of x is not increasing. Do you remember the example? It was one example in the lecture. Does anyone recall that? I don't exactly recall that. So, okay, let me, once again, let me just pull that up. It will be good to record that here. So, where was the, not able to locate that. So, if anyone is able to locate that, just let me know. Okay.
So
Those,
g of x equal to x square and f of x equal to e power minus x.
okay. Uh, so g of x equal to x square, is it?
Yes, sir.
And f of x equal to
E power minus x.
okay, e power minus x is also is not increasing, right? It is decreasing. So e power minus x. Okay, so then h of x is what? F of g of x. So e power minus x square. Is that correct?
Yes, sir.
Okay, so e power minus x square. Yeah, that is nice. Yeah, that's a good example. Okay, so to see the importance of f being a non-decreasing function, consider this, right? So f of x is e power minus x. So e power minus x square, you have to remember the bell-shaped curve, right? So what will e power minus x square be? It is in fact e power minus x square. It's like a normal the bell-shaped curve, right? So this is e power minus x square, and clearly this is not convex, right? So e power minus x square. This is h of x, right? And this is clearly not convex. In fact, yeah, it's neither convex nor concave, right? Because if you draw a line here, line segment that will be above here, above the function. If you draw it here, it will be below the function, and so it's neither convex nor concave, right? So this is important. Okay, so that is f and g composition.
Sir, can you please draw e to the power x square?
Okay, e power x square will be e power x square. Yeah, that apparently this is how it looks. It's a symmetric function, even function.
This is convex, right?
Yeah, this is convex. Yeah. So any line segment that you draw, the functions below the line segment. Okay.
But sir, fx in this case is decreasing also.
No, right? F of x is increasing. So e power x is an increasing function. So e power x will look like this, right? So e power x is this is e power x, no?
I mean g of x.
G of x is, there's no condition on g of x, right? G of x, it's enough if it is convex. It is only f that has to be non-decreasing.
Okay, thanks.
Okay, so that is property 3.
Excuse me, sir.
Yeah.
So one question, I was seeing this function, so I remember. If you plot in GeoGebra or Desmos a curve that has been discussed in lecture 9, that was x square plus 2x2 plus 4x square, x1 square something. Whatever we have been told in the lecture that this would be the maxima, that would be the minima, when you really plot the curve, it's totally different.
Which curve is it? Which function is it?
It's a kind of a parabolic function in 3 dimensions. We lectures of week 9 most probably have used it extensively for positive definiteness and negative definiteness of that.
Okay, so can you look that up and let me know? I'll keep, I'll continue, but
Yeah,
yeah.
I'm seeing.
Yeah. Okay, so that is convex, the composition. The other property is this particular composition. It becomes it is always convex if your function g is a linear function. So what I mean by I've written the word affine. So just a note. So an affine function is nothing but a linear. It's not, so it's better to call it affine and not linear. As an affine function, it's a function f or g, okay, from Rn to Rn to R, and is of the form g of x equal to w transpose x plus b. Okay, so this is, or a transpose x plus b. So what will it look like? So if you expand it, it'll just be a1 x1 plus a1 a2 x2 till an xn plus b, right? So it's a linear. We don't call it linear because from the linear algebra point of view, this is not really a linear function. It's not a linear transformation. It's an affine transformation, right? So you are kind of adding this extra constant here. So that is so note on affine functions. This is like this. This is a small note. By expanding this, you get this, right? It's like expanding the RHS. This is what you get. So an important property of affine function is what? An important property of affine functions is the following. So if you have g of lambda x plus 1 minus lambda y, okay, what is this equal to? Does anyone know what this will be equal to?
Lambda of g of x plus 1 minus lambda g of y.
Correct, right? So that is the property. So you can actually very easily see this. So you just have to plug in x plus, so lambda x plus 1 minus lambda y here in the place of x, and you will see that it nicely factors into g of x plus 1 minus lambda g of y. So notice that this is what this is like the
Hello.
yeah, you are audible now.
Yeah, sorry. So actually, I wanted to just ask this. I read somewhere that the property is somewhat like g of lambda x plus 1 minus lambda y is less than equal to lambda times g of x plus
Correct,
1
but
minus
that is for a convex function in general. What we are discussing is these
affine.
functions called affine functions, which are a particular type of convex functions,
Okay.
right? So these are like linear. These are like lines. So for example, your g of, if x is two variables, right? So it could be x comma y equal to 2x minus 3y plus 4. Okay, something like this. So this is a plus 5. So this function is a affine function. This is convex. So this is like a linear. So all affine functions are convex. The problem is they are
Okay.
also not problem.
But it is
They are
still
also
two
concave.
dimensional.
Sorry, can you
Okay. It
repeat
is a
that?
linear. It is a linear function, but
Yeah, it is a
since it's a
linear.
linear function.
Yeah, you can call it a linear function. Yeah.
Okay. So if I plot two vectors x and y, and then perform these operations on a functions like this, then it will travel across the functions. Uh, that is what is meant, right?
So see, what is meant is So if you plot this, right, so this is like 2x. So that is what 2x minus 3y plus 5. So this is like 3y equal to 2x, or y equal to 2x minus 5 by 3, right? So 2x minus 5 by 3. This is what is the function. So now this is what is an affine function, right? So what I am saying is, if you take any 2 points and connect them by a line segment, any point on that line segment, the function's value will be exactly equal to, yeah, not less than or equal to in the general case, but equal to. So that is a property of affine functions, linear functions, right?
Okay. Yeah. Got it. Thank you.
Yeah. So yeah. So if the function is affine, it is also convex, by the way. But if it is like a very strong restriction, right? Then f of g is convex. You don't need f to be increasing, non-decreasing, and all that, right? So if in the special case you have f of g to be convex. So for example, you have, let's take any affine, let's take any convex function f of x equal to, once again, say the famous e power x, right? And g of x equal to, but g f of x is e power x is increasing, so let's take something like x square, right, which is not strictly increasing. It's not non-decreasing, right? So it decreases and then increases. And g of x equal to 2x minus 3, right? Then f of g of x, right? So f of g of x in this case is nothing but 2x minus 3 whole square is also convex. That's the idea. Or maybe something else, like what could be a good example of maybe mod x, right? So mod x also is very similar. I need to have like better examples of convex functions. These two are very, always we are going back to e power x and x square. What else can we think of? Something that's slightly non-trivial.
Negative log of x.
Yeah, negative log x is like increasing, right? Non-decreasing, right? So it will anyway hold good. Okay. So you are saying f of x can be negative. Yeah, that's, I can use f of x to be negative log x. So that will work. And g of x could be anything, right? So 5x minus 7. Okay. Therefore, minus log of 5x minus 7 will also be convex, right? So that's the idea. Okay. Then, of course, you have to be careful about the domains. So minus negative log of 5x minus 7 is also convex. So maybe when I upload this, I will try to add a few more examples which are slightly more complex. Okay, so that is regarding composition. So the other thing which is very, very important, right, which is like the most important property is this. So if f is convex, then every local minimum of f is also a global minimum. Okay, so the proof is there in the lectures also. I've just redrawn the same image that is there in the lectures. So please refer to the lectures or this document later on for the proof, right? So the main part is that convex functions are extremely convenient when it comes to optimization, because if there is a minimum, it can only be a global minimum, right? So there is, and there cannot be two global minima, there cannot be two minima with different values of the objective function. Okay, so that's the idea. So if there is a minimum, if you have found a minimum for a convex problem, a local minimum, then you're like done. So you don't have to think about anything else. You have solved the problem. Okay, so now examples very easy to see. Our usual examples. For example, f of x equal to x square has a local minimum at x equal to 0, which is also its global minimum. So same is the case with uh, mod x, for example. We look at problems where this is not the case. So meaning there are no minima, right? So I'll discuss that in the next section. But if a minimum exists, then it has to be a global minimum, right? So that's what we are saying. So you have to be careful. I'll come back to this point in like 5 minutes. Okay. So Yeah, that is regarding local minimum being the global minimum. So what else do we have? The set of all local minima is a convex set. Okay, so meaning if there are multiple minima that a function has, they're all going to be global minima, and the set formed by them is actually going to be a convex set. So for example, uh, consider the following function. So consider f of x equal to, it's defined piecewise, so it is like 0 when x equal to, and like 1 less than or so minus 1 less than or equal to x less than or equal to 1, it's 0. And then it starts with x minus 1 whole square when x is greater than 1, and it starts with plus 1 whole square when x is less than minus 1. So minus 1. Okay, so if you plot this, so it's what? It's 0 from, we plotted this function last time, but it was quite some time back. So between minus 1 and 1, this is 0. Okay. So between minus 1 and 1, this is 0. And it is x minus 1 whole square when it is beyond 1. So 1 to, let's say, infinity, but then I am just using it for 10. Okay. And then when it is less than minus 1, it is x plus 1 whole square. Okay. X plus 1 whole square when it is less than 1. So specify range, let's say it's from minus 10 to minus 1. Okay. So this is the function. Now for this function, where is the minima for this function? Where are the minima rather?
Between minus 1 and 1.
Yeah, so this function, first of all, you have to notice that this function has infinitely many minima, right? Okay, infinitely many minima, and all of them, so infinitely many minima, and the set of all minima is the interval minus 1 comma 1. Okay, so, and main thing, what is this property? This, if f is convex, then the set of all local minima of f is a convex set. That's what we are here to see, right? So, and notice that minus 1 to 1 interval is a convex set. Okay, so that is what this is really trying to show, that the set of all is an example of this property. Set of all minima for a convex function, okay, is itself a convex set. All right, so this is you can think of the generalization of this two, three dimensions, or rather two functions of two variables. You can think of a bowl, right, which has a flat bottom. Okay, if you have a bowl with a flat bottom, then maybe a circular flat bottom, then that circle is the bottom, right? The bottom of the vessel, which is a circle, forms the set of all local minima or set of all global minima, and that is a convex set. Okay, so I hope you got that idea. Okay, so flat bottomed vessel, the flat bottom is the convex set of all local minima. Okay, so the final thing, once again, very useful property is that if f is differentiable in addition to being convex, then you can find out the global minima by just looking at its gradient, setting its gradient to 0 and seeing where it becomes 0. So notice that you can't do this for any function. Are you all able to see this? You can't do this for, let's say, some random function, right? So which is not convex. If the gradient is 0, there is no guarantee that x star is a minimum. Okay, it's only a stationary point or a critical point. So property 7, you have to be careful. Note that for a function in general, okay, if gradient of f of x star equal to 0, all that we can say is that x star is a critical point of f, or also stationary point in this case. Okay, we can't say whether it is a maximum or minimum. It could even be a saddle point, right? So you have to be careful. But if it is convex, then remarkably, what we can say is that if the gradient is 0, if it vanishes, then x star is a global minimum, not just local minimum, but global minimum. Okay, is this clear? These properties, these 7 properties.
Please repeat the last property.
Sorry?
Please repeat the last property. Actually, I couldn't get it the first time.
Yeah, so this is the statement. You are clear with this statement is clear, right?
Yes, it's clear.
Yeah, so this is what I'm saying in the remark is that this is not true for any function. Okay, for example, if the classic example is if f
If
of
it's
x
not
equal,
convex, basically.
yeah, if f of x equal to x cube, then so gradient in
The-
this case it's just the derivative. F of 0 is 0, but x equal to 0 is not a minimum, right? So that is
So,
the, yeah. So you can, this is because f is not convex, right? So this is because
so
not because
because
f is not.
we are considering convex functions because we want to take like we want to constrain apply constraints over the function, and that is why we are considering convex functions so that linear
So we are
combinations between any combination in that area in that space will be will give another point in that space only, right?
that is the definition, but yeah, we are looking at convex functions because they are so well behaved, right? So for example,
Okay.
just this property alone is enough for us to study convex functions, right? This is like
Yes. Yes.
very surprising property because not many functions have this. Even something as well behaved as x cube, differentiable infinitely many times, continuous, all that, but still it doesn't have, you can't find the minimum. It doesn't have a minimum, that's a different thing, but you can't find the minimum by just setting the gradient to 0, right? So
Yeah. So in case like in convex functions, basically there is a plateau. Like I'm sorry, there is a valley.
yeah, there could be a valley, right? So next section we look at why we have to be careful about convex functions and this last property. So yeah, so there is, you have to be careful. Now this
But even in x cube, we can create a convex function like removing one part, the negative less than 0 part. Then kind of will it be a convex function?
if you remove the
Mm,
we'll have
x
to,
less than 0.
yeah, if you remove
X and
x less than 0, yes, yeah, 3x square 6x, yeah, as long as
I
x is
mean,
greater than 0, yeah.
will it be ideal? I mean, can it be doable? Like, can we consider it? Can we constrain x cube in that way and then consider it x convex function? If,
Yeah,
is
so
it
as
right?
long as you can, that is convex. So f from 0 to infinity to r, f of x equal to x cube is convex. Yeah, you can do that, but depends, right? If your application where you are using this should allow you to do this. As long as it allows you to do it, I think you can do it.
Okay. Okay. Sorry. Yeah. Yeah. Fine.
Okay, so the local minima implies global minima is a careful, you have to use it very carefully. Okay, you can't like, you should not misunderstand the property. Now, what does that property tell you? This is property number 6, right? If a convex, if no, not 6, 5, right? So if this is the property. So if f is convex, then every local minimum is a global minimum. So recall the property. Okay, if f is convex, okay, this is the property. Now, this, if f does not have a minimum, then this property doesn't come into play. Okay, notice that. So if f is convex, that is there. F can be convex, or so that is not our issue. But f should have a minimum in the first place. Okay, if it has a local minimum, then this property comes into play. If f does not have a local minimum, then you can't say that by using this property there should be a global minimum, right? So what I'm saying is this property doesn't guarantee that every convex function has a global minimum. That is not what this property is telling you. Okay, in fact, every convex function needn't have a global minimum at all. Okay, so examples are very obvious. Examples are e power x, right? So e power x does not have a minimum. As x tends to minus infinity, it tends to 0, that is there, but it never achieves 0. Okay, another example is f of x equal to x, right? So f of x
Yes,
equal to x.
sir. Sorry to interrupt. I want to know whether in this case, in which this is an asymptote, I will consider it as a convex function or not.
The asymptote has nothing to do with convexity.
No. I'm just saying this e to the power x asymptotes to 0 at infinity. That is what I said.
Correct, but that doesn't affect convexity, right? It only.
So I will consider it as a convex function or not.
So why do you think that the asymptote should meddle with the convexity?
No. Actually, what I mean is that it is going to 0 at infinity. So 0 is its minima. It has one minima, which is a local and a global. It is 0. So I can call it a.
No, that is what I'm trying to say, right? It does not have a minimum. So that's the whole point. So
Means so it is not a convex function.
no, it is a convex function. That is the main point, right? So every convex function need not have a minimum.
Okay.
Right? So e power x does not have a minimum, but it is still convex. So it is still convex. More importantly, this property cannot be used. So this property that local minimum is a global minimum can only be used when the function has a minima in the first place. Okay. So same with f of x equal to x. So this is like this is convex and concave, but clearly this does not have a minimum, right? So there's no question of global and local. This is the function that we plotted. So this is useful for another reason, to demonstrate another fact that. Okay, sorry, I went too big. Where is this? Yeah. So the other fact or other remark is that a function could have multiple minima. Okay, so this is another important point. This property is not telling you that a convex function has only one minimum. No, that's not what it's telling you. All that the property is telling you is that every local minimum is a global minimum, right? So a convex function would have multiple minima, but the value of the function at all the minima is what? Is the
global minima. That is it.
The same, right? It's the same, and it is equal to the global minimum value, right? So okay, so please make a note of that. That's what this example is telling you. It's telling you that there are infinitely local minima, many local minima, but the point is all of them have the same function value, right? So function value is 0. Okay. So yeah, those are the points you have to be careful about when using this particular property.
Sir, if we consider the range 2, 3 in this graph, then the local minima is at 2, but its value is not equal to that at global minima.
But yeah, it is, right? So you are changing the function itself, right? Altogether. So for example, if your function is f, you have to define the function appropriately. So you're saying this is the function, right? Where f of x equal to x plus 1 whole square, correct?
Yes.
This is your function, right? So now this is let's call it g of x, right? So this is not the same as f, no? So this is not the same as f. So if you plot this, you will get what? You will get, you will only retain the right arm. So this is not there. This is not a part of the function anymore. So this is the function. So the function now becomes from 2 to 3. So 2 is a global minimum. Okay. But it's
So
not a
g
local.
of x is x minus 1 whole square. G of x.
Sorry. Yeah. X minus 1 whole square, right? So now, yeah, what is your point here? So
So we should not consider like the function f to apply here. Instead, consider g to
g,
apply.
yeah, exactly. Yeah. So this is a different convex function from f. Okay. So, okay, this is actually a nice example of a function which has no local minimum, right? It has a global minimum, but it does not have a local minimum. Okay, so in fact, this also can be another caution. So there could be functions that have a global minimum, but no local minimum. Okay, so this is one example. Another example is classic example is what?
Sir, can we say that that this gx is a concave? Sorry, that this gx is a convex function.
This is convex, right? This is 2 to 3 x minus 1 whole square is convex. So f double prime of x, so g double prime is greater than 0. It is 2, right? Therefore, it is convex. 2 to 3 is a convex set. So it satisfies all the conditions of convexity, right? So it is a convex function.
Okay.
So is it? So
Yeah.
can we say that we can convert any concave function into a convex function or a combination of convex functions and optimize them for accordingly?
Any
Or
any concave function, you can negate it, and then that will become convex, right? So
yeah, and we
so
can
any
solve for optimal and minima. Sorry, minima.
minimum. Sorry, can you repeat? I didn't get why. Why are you bringing in concave here?
No, since this is not constrained, we have constrained this function and found the minima, global minima for this function. So
Right.
similarly, I was thinking that like most of the application, most of the ML models are based on convex functions only. So that is why I was thinking that yeah, maybe we use concave functions also, but like we convert concave function into convex function also, and then try to optimize it. That is I was trying to link with it.
Okay. Right. But concave is it's like just the
Okay,
mirror image in some sense, right? So once you study convex functions, you're like as good as studied concave functions also, because it's just a sign change, right? So whatever works for f of x, if g is concave, then you can just do minus g and apply whatever you have learned about convex functions. So right.
okay, okay.
Right. So in fact, no, this is not a correct example. So this is wrong. So what I said is, see, this is still a local minimum. It's just that it is not differentiable at this point. So I'll correct my statement. This is not. So every global minimum is naturally a local minimum, right? So it can't be otherwise. So there could be functions that have a global minimum. Okay. So this in fact this is not an example for anything. Okay. So this is like, perhaps what I should say is there could be functions that have a global minimum where function is not differentiable at that point, right? So which would mean that, so this is like a counterexample, not counterexample strictly speaking. This is like property 7 when f is differentiable is taken out, right? So what happens in that case? You could have like mod x, right? So for example, mod x is a convex function for which the function is, there's a global minimum at 0, but you can't talk about gradient of f at 0. Okay, that is a valid example. This is what I wrote before is wrong. Okay, so this is x equal to 1, x equal to 2 is a global minimum. It is also local minimum. Only thing is that you can't consider any interval to the left hand side, right? So you can't consider what happens to the left of 2 because that is not even there in the domain. But still, it's still a local minimum only. Okay, it's both global and local. That's what I meant to say. That's clear, right? What I wrote earlier is not correct.
Yes, sir.
Okay, so every global minimum is also naturally going to be local. So, okay, so that is there could be convex functions that have a global minimum where the function is not differentiable at that point. Okay, this is one example. So let's complete this. For example, this is f of x equal to mod x. Okay, yeah. So now that takes us to inequality constraints. Okay, so this is, we have already seen inequality constraints. So inequality constraints is what we'll concern ourselves with. And for equality constraint, just to remind you, what we did was we have the function, we have g of x comma y equal to 0. We can construct the Lagrangian f of x comma y plus lambda g of x comma y. We set the gradient of the Lagrangian to 0, and that gives us the method of Lagrange multipliers. We solve for x, y, lambda, we eliminate lambda, or we do something right along those lines and get x comma y. So that's a necessary condition. If you remember, it is, there is no guarantee that the Lagrange multipliers will actually lead you to the minimum, okay, local minimum. It's a necessary condition, meaning it, if it is a minimum, then the Lagrange conditions, the gradient of L is 0, all that is satisfied. Okay, so that's what we saw for equality constraints. So inequality constraints, what are they? You have, let's just look at one inequality constraint. So this is what I have drawn is a representative diagram. So anything inside this region is a feasible point. Okay, so whatever I've shaded here is the set of all feasible points, meaning the constraint is satisfied. This is the boundary. Okay, so you can use these terms. This is the boundary of the constraint. It's the boundary of the constraint, and it's small. This is the interior of the constraint. Okay. Now, both the boundary and the interior are part of the constraint. In this case, notice that the boundary is not a part of the constraint. Only the interior shaded region is the part of the constraint, right? So this is the feasible region. Without the boundary is the feasible region. Okay. So that's the difference between a strict inequality constraint and less than or equal to. Okay. So that is something you have to keep in mind. You should also know inequality versus equality. So inequality constraints usually are regions closed, not necessarily closed, but regions in R2. Okay. Equality constraints are more of curves in R2. Okay. This is equality, inequality. So region, curve. The next thing you have to know is constraints can result in unbounded regions or bounded regions. So this is an example of a bounded region, which a constraint gives you. Okay, so here you have, it's the negative of this constraint actually. This is g of x comma y greater than or equal to 0. So that is nothing but all of space except this elliptical hole. Okay, so everything outside this ellipse is a part of the constraint region. So this is an unbounded constraint because it has infinite area, right? So you can, it's like all of the space, but for the ellipse. This is the inverse of it. So all of ellipse, but it's bounded. Okay, so you could have constraints of this form. You could also have linear and non-linear constraints. So what is there on the left is a non-linear constraint. Okay, so this will be some x squared by a square plus y squared by b square less than or equal to some number. Okay, so that is an elliptical constraint. This is a linear constraint. So it is of the form
Sir, is this g of x comma y less than 0, can we call it as a level curve of a
Equal to 0 is a level curve. Less than or equal to 0 will be a region.
Okay, okay.
Right? So the boundary is a level curve, but not the actual region, right? So inside the you'll have different values. So you could plot multiple level curves, for example, not as so this if you just make it, you know, something smaller. So this is going to sit inside. This will have g of x comma y on the boundary something less than 0, say -1, -2. So you could plot level curves within this, but then this boundary itself is only one level curve of g.
Okay, not the region inside the
Region
shaded.
inside is not a level curve, so it's Okay, so maybe I should yeah, that's fine. So linear, you understand, right? So this is like a half space. This is called a half space. So half space is like you are dividing the space into two parts, and once again, we should this is like on the boundary. So if this is less than 0, this would be a dotted line. But if it's equal to 0, then any point on the boundary is also part of the constraint. Okay. So these are linear and nonlinear constraints. These are often called affine constraints also. So is this fine? The general picture, so that I can move on to examples. Okay, we'll now look at three very specific examples of what they are. So this is like y minus x less than or equal to 0. Okay, so how does this look? This is going to look something like this. So if y minus x is less than or equal to 0, y is less than or equal to x, correct? Okay, this is the constraint. So whatever is the shaded region, these are all feasible points. So any point here, let's say 10 comma minus 5. So we'll add some points. So 10 comma minus 5 is a feasible point inside. So because it's sitting inside the constraint. Okay, so this is a half space. Now this is once again a half space. Okay, this is an affine constraint. All right, so that is example 1. Now example 2. What do you think this will look like if I plot it? Before I plot it, I want to ask you, g of x comma y less than or equal to 0, how will it look like?
A convex function of the parabola having a y is equal to x square. The epigraph of it is
correct. That's correct. Very good. So it'll look like the epigraph of y equal to x square. So this is in fact greater than or equal to x square, right? This is how it will look like. So x square less than or equal to y. What is this? So x square less than or equal to y implies y greater than or equal to x square, right? So sorry, yeah, x square, which is like, can also think of this as the epigraph of f of x equal to x square. So all these points which are above x square. So once again, you can add some feasible points, and this is an example of an unbounded region. Both of them are unbounded.
Here gx y is equal to 0 in this case.
No, less than or equal to 0. Always. So always the convention is g of x comma y will be less than or equal to 0. Okay, so that is unbounded, right? Both of them are unbounded. We look at one more. So what do you think this constraint will look like?
This is actually the origin, the point. No. It is not a point. It is a circle of radius 1.
Correct.
Circle 1.
Correct. Yeah. So it's a circle of radius 1. So yeah. So this is a circle of radius 1. So let me draw the axis and circle. Okay. So this is the constraint, and you place it here. So everything. So you have to shade it. Okay. You'll have to include the so should the boundary be included or not?
Yes, sir. It's
less than equal to 0 may included.
Correct. Yeah, it's if it is an inequality with an equal to sign, it has to be included, right? So this is this is a this is the constraint for this case. Okay, x square plus y square minus 1 less than or equal to 0. So it's a circle with radius 1. So those are constraints. Now I want to talk about this particular point called active and inactive constraints. This is not a part of the lecture, but it's useful. It's important to know. It's useful to know because it's like it tells you little bit more about an inequality constraint. Okay. So think about this g of x comma y less than or equal to 0. This is the region. Okay. So this is the region. Now, what can you say about these 2 points? These are 2 different points which are feasible points. What can you say about them? Or what is different about them?
they are a convex set by itself.
Okay, so this is if G is convex, it is a convex set, but right, but not that's not what I'm asking. So what I'm asking is these blue points are there, right? They are. What all can you say about them?
One is on the border and another is inside the.
Correct. One is on the boundary, other one is strictly inside the constraint region. So therefore, what do you conclude?
Sir, if we remove the equal sign here, so the point it is in boundary, it will not will be in constraint part if we
Correct.
remove this equal to sign. So only the blue dot that is exactly middle of the diagram, that will be active constraint, or that should be the main constraint that will not change.
Okay. So if I call this, if I call the blue point x1 y1, okay, and I call the maybe this. Let's make this red point, right? So in fact, it's better to make this green for reasons that will become clear soon. So I'll call this x1 y1. I'll call this x2 y2. What can you say about g of x1 y1 and g of x2 y2? G of x1 y1 is what?
It's equal to 0.
It's equal to 0. Correct. Yeah, that's good. So g of x1 y1 is 0, and g of x2 y2 is
Less than 0.
yes
Less than.
less than 0.
Less than
Right?
equal to 0. Less
So
than 0.
yeah, so this is the important part. So this is when this happens. When this happens, right? When the constraint, when the point lies on the boundary. Okay, when g of xy is 0, we call that an active constraint. Right, I'll write it down here.
It's 9 o'clock.
And when it lies strictly inside, and so it's called an inactive constraint. So this, or rather, what you can say is the constraint is active here, and the constraint is inactive here. Okay, so to understand why they are using this terminology, remember that. So if you move this point slightly, right, if you perturb it, the constraint doesn't change. Okay, rather, so nothing is going to happen. So it's like lying dormant in some sense. So it's inactive. But if you perturb it slightly here, what might happen? If you move it in the wrong direction, it will violate the constraint, right? It will exit the feasible region. So those points which are on the boundary, in fact, are very important. So they are active. It's like a sensitive region. The boundary is a sensitive region, and if you perturb things slightly, you are going to go out of the feasible region. That's not the case for points which are strictly inside, which are points like this, right? For which this inequality is strictly less than 0. Okay, is this clear? This idea of active and inactive constraints?
Yes, sir.
Yes, sir.
Okay, so right. So we will just take some 2 minutes. Let's just break for 2 minutes and I'll come back. We'll continue with this feasible directions. Okay. Okay, so yeah, we'll resume. So we now start looking at feasible directions, right? So in the case of equality constraints, we had only two directions which were feasible, right? So if you have G like this, then this is the gradient of G. So what is it telling you? The point you're, in fact, let me add the point here. So this is an active constraint, right? So you're adding, let me add a point at the boundary of the constraint. So this is the point of interest. And you're asking what are the directions in which I can move from the green point where I will continue to remain in the feasible region. Okay. So the gradient is pointing perpendicular to the contour at this point. Okay. The gradient is always perpendicular to the contour. What do we mean by that is if you draw a tangent to this curve, then the gradient will always be perpendicular to that. Okay. So that is point number one. Point number two is if you move in the direction of the gradient, or if you move in the direction that is making an acute angle with the gradient, the function's value will increase or decrease.
Increase.
Increase, right? So any movement in this region, okay, this entire region, if you try to move, the constraints value will increase. So here the constraint is 0. And if you move away in any of these directions, the constraint is going to increase by some amount. So it will no longer be less than or equal to 0. It will be strictly greater than 0. Okay, so these are all bad directions of movement. What is the direction of movement that will ensure function's value either stays constant or decreases? It is either along this direction, which is perpendicular to del G, or makes an obtuse angle with del G. Okay, so that those are the only feasible directions. So that's what I've like removed the constraint, and I'm only showing the set of all feasible directions. So this is like anything here, right? So any direction here is all of these are feasible. So they will result in the constraints value decreasing. And since you're on the boundary, so you start with this active constraint, meaning you're on the boundary. This is an image for the active constraint part. Okay. This is clear, right? This is covered in the lecture. So I hope this is clear to everyone.
Yes, sir.
Okay, so now let's quickly solve one question. So question is this. So find the set of all feasible directions at the point 0, 1 for this inequality constraint. Okay, so how will you approach this problem? You have to find all possible feasible directions. What is step 1 that you will do?
Find gradient at point.
Okay, that is correct. But even before that, can you do something? Can you visualize this?
It is a circle less than 1 radian.
Okay, so it's a circle of radius 1. So step 1 is maybe you will plot this. So it's you can't, of course, you're right. You can't do it always. So this is like not always. So plot the constraint. In this case, it turns out to be circle radius 1. Yeah.
Sir, as we learned that gx must be less than or equal to 0, so we can write it like this: x square plus y square minus 1 less than equal to 0.
Correct. Yeah, that is how you should write it. Yeah. Okay. So plot the constraint and the point of interest. So the point of interest in this case, I'll take this green color point from here. Where is it lying? Can you tell me where the point of interest lies?
On the y-axis.
Should it be here on the y-axis, right? Exactly right at the top. So that is 0, 1. So that is the point of interest. Now, okay, so I'll like step 1 and all I will not do. So I think I'll have to duplicate these images, but I hope you get the idea. So visually, what will you do next?
Draw a tangent to it at that point.
You draw a tangent to it at that point.
Yes. And the half point plane pointing downwards will that which is within the circle, only these are the feasible directions.
Correct. Yeah. So that is the geometric idea, right? So now we'll come to the algebraic justification. So so we have to compute the tangent, right? So tangent at 0, sorry, the gradient at 0, 1. So what will that be? The gradient of first of all plus g of x comma y is x square plus y square minus 1. Okay. The gradient of g at 1 or 0, 1 is what? 0, 1 is del g. What will it be? 0, 0, 2, correct, right? Is that correct?
Yes, sir.
0, 2, okay, yeah. So 0, 2. So you can also plot that. No harm in doing that also. So you can look something like this, right? So maybe this, I'll just make it bigger. Yeah, so this is 0, 2. So this is del g. So del g is pointing in this direction. So yeah, now for the final step, right? So how will you write down the set of all feasible points? The set of all feasible points are, it has to be a set, right? So it has to be some set builder notation, some set of points for which something happens. So what will that be?
X square plus 1 minus x squared is less than equal to 1. Is it something like that?
So first of all, what will be a member of the set? Sorry, the set of all feasible directions, right? That's what the question is, are not feasible points, the set of all feasible directions. Okay. So in fact, I should have made it clear, ensure that all directions have unit norm, right? So you're only interested in direction, not magnitude. So it's enough if they're all unit norm. So now tell me.
All direction in which gradient is equals to the negative of the gradient.
All directions in which D in which
del g equals to negative.
Okay, but then there's only one direction in which D is negative of del G, right? That's like just opposite to G. So this direction won't come in there, right? So how do you include something like this? So if what is happening to this direction, this is a valid feasible direction, right? So what is the relationship between D and del G?
It is deviated with some angle. So is it something related to angle?
Angle, yeah, it is related to the angle. So what is it about the angle that happens here?
It's obtuse angle.
It is obtuse angle. So how do you express that in terms of operations you are familiar with?
Slope.
So if the angle between two vectors is obtuse, then what can you say about what?
Its dot product is negative.
Correct. Yeah, its dot product with del G is negative, right? So the set of all feasible directions are those directions D for which D transpose del G equal to is less than or equal to 0. In this case, equal to is okay because you can also move perpendicular to del G because the constraint is equality constraint, less than or equal to constraint, right? So this is the set. Okay. And you should also add for extra measure that norm D is 1, right? It's like unit norm. So this gives you an equation inequality again. Okay. So let's say let the direction be say x comma y. Then what is D transpose del G going to give you? What is del G? 0, 2, right? So it is x into 0 plus x into 0 plus
y into 2.
Y into 2 equal to less than or equal to
0.
0, right? So this
That means
is
2y less than 0.
Yeah. So this is y less than or equal to
1 by 2. Sorry, 0.
0, right? So now x can be what? There is no constraint on x, right? So x can be anything. So
Anything, yeah.
anything, right? So therefore, I can write down d as some x comma
Negative values, only
some negative value, right? So let's say this is, for convenience, let's call this -1. Okay. Now, if I want d to be unit norm, what will it be? What should d be?
Exists.
0, -1.
But that will give me only one direction, right? Exactly opposite to del g. So I want, if I want to normalize d, what will I do?
Divide by square root of x square plus 1.
Yeah. So this is a unit norm vector. Okay. So depending on what x is, this will be, what will this give you? This will give you all possible directions, right? So I can write down the set as the final set, therefore becomes the set of all d. This is the actual set, but I can write this as set of all points of the form x comma -1, x square plus 1, where x is in R. Okay. So what do you think this should look like? So if you call this x1 comma y1, right? So if this is confusing, if this is a bit confusing, let's work it out a bit more. If you call this x1 comma y1, so x1 is what? X by under root x square plus 1, and y1 is what? Or not x1 y1, let's call it x prime y prime, let's say. So this is like, this is what? 1 by -1 by x square plus 1. Okay. This implies, what can you say about x prime square plus y prime square?
1.
This is 1, right? So this is actually what? What kind of an figure is this? It's a curve, right? It's a curve. What kind of a curve is this?
Circle.
It's a circle.
Again, circle. Yeah.
But is it a full circle? Y is always negative. So what will this be then?
Semicircle.
Semicircle, exactly. Right. So that's what the final picture should look like. So if you actually draw this, the set of all feasible directions is nothing but a semicircle. So does this fellow have a semicircle? Yeah, he has. So it'll look like this. Okay. So this is like, this will finally go and sit there. Let's make it slightly bigger. Okay, so this will be your feasible directions. Now this D will be one such feasible direction. Okay, so
Sir, here, what is the length of D? Is it 1 by square root of x square plus 1?
are you able to hear me?
Yes, sir. Sir, here, what is the length of D here, sir? In the
yeah, length of D is 1. So I think I lost you somewhere. My network connection got disrupted for a while. So
no problem. Yeah.
this till this part it was clear, right? Hello?
Yes, sir.
Yeah, okay. So this is clear, no? Now what? So the set of all feasible directions are these directions, right? So every vector that is on the semicircle is one such direction, which is a feasible direction.
Sir,
And
if D length is 1, the semicircle should touch at the.
Yeah, it should touch. Yeah, this should actually touch.
Yeah, touch the center of the circle.
Center of the
Because you said d length is 1, right? So,
oh, okay, you are right. Yeah. So you are right. So yeah, it is better to draw it to scale. So correct, you're right. But so assume that if you what you're interested in is in the direction and not magnitude. So I have not drawn it to scale. So this I just mention it here. So semicircle not drawn to scale. Only directions are shown. Okay. Is that fine? I'm just showing the directions, but you're right. In reality, it should touch the center of the circle. Okay. Is that fine?
yes, sir. So final solution should be for 0, 1 point. What are the feasible solutions is all the points that are lying under the semicircle which we have drawn. Is my statement correct?
Correct. Yeah. Those are the directions. Yeah. So they are not the feasible points. They are the directions. They are the feasible directions that you can move from 0, 1 given this constraint. Okay. So we have to be careful about feasible directions and actual feasible points, right? So for example, if I move along this negative direction with the magnitude of 5, right, I will go outside the feasible region. So whenever we say feasible directions, what we mean is by a very small distance in that direction. Okay, so that's the idea. So is this clear? This is clear, right? Whatever we have discussed so far, all feasible directions. Okay, I hope it's clear. So I will move on. Okay, so now this is the image you have to keep in mind for a direction which is feasible and descent, right? So that's what we have to avoid. So what are we looking at? What are we trying to understand now? This is the question that we are asking. So question is, what does local minimum of an unconstrained optimization problem look like? So meaning if X star is a local minimum, then what can we say about, say, maybe gradient of F and gradient of G? Okay, so things like that, right? So what does it mean if something is a local minimum? So what have you learned from lectures? If X star is a local minimum, then there should be no direction, no dash direction that is also dash. So how will you fill this?
No feasible direction.
No feasible direction that is also
Minimum.
that is also something else, right? There should be no feasible direction that is also a
Descent direction.
Right? So you should not be able to descend along some direction where the function's value decreases, which is also feasible. That's the whole idea. Okay. So now that's where these pictures come to our rescue. So remember that if you go along this direction, the constraint will increase, but our constraint is less than or equal to 0. So this is like a boundary. So active constraint means you are sitting on the boundary. Once again, I'll take this green point. What's that green point? So this green point is sitting here. Okay. So you're talking about del F del G on this green point, which is on the boundary. So this green region is a feasible region. Okay. So that's what we saw here. So here also that's what we saw. So this green region, if you move a small distance anywhere here in the green region, you are safe. You are still in the feasible region. But if X star is a minimum, then so for this image, can X star be the minimum? So if this is X star, this green point is X star, can X star be a minimum here?
No.
No, right? Because you have a feasible direction for namely this one example, which is also a descent direction. So why is this a descent direction? This is like the all directions. The red color is all the descent directions, right? It's opposite to gradient of f. So anywhere here the function's value is going to increase, but anywhere in the red region, if you move, the function's value will decrease. So you have a feasible direction, which is the intersection of, so a feasible descent direction is what? The intersection of the red region and the green region. So you have so many directions to move. Anywhere starting from here and ending here. So you'll get this arc, circular arc, right? There are so many directions which are feasible descent directions. Therefore, this can't be a minimum. So if you have to have a minimum at this point, if someone claims that you have a minimum, this is the only way that can happen. Okay, so remember that green is feasible. So constraint is pointing here, the constraint's gradient. So if you go in this direction, constraint will reduce. So these are all feasible directions. The gradient is of the function, objective is in this direction, and anything opposite to that or like with obtuse angle to that, function's value will decrease. So these are all descent, and they have nothing in common. Okay, so this is the example of there is no feasible direction, or rather there is no descent direction that is also feasible. Okay, and this is what we want, or this is what should happen if X star is a local minimum, right? So if X star is a local minimum, then what can you conclude? Then the gradient and the gradient of the function and the objective are
Anti-parallel.
yeah, the gradient of the function, objective function, and the constraint at X star are anti-parallel, meaning there is some lambda greater than 0 such that greater than perhaps equal to 0 such that del F is
Minus lambda del G.
lambda del G, correct. Okay, which implies that from this it follows that we can, what can we say? We can say that del F plus lambda del G at X star. Okay, so let's better make this at X star. Sorry, this is del G, right, at X star. So del F at X star plus lambda del G at X star equal to 0. Okay, that's one thing that we are able to say, equal to 0. And we are also claiming that this happens for some lambda greater than 0. Okay, now let's maybe use lambda star. Okay, some lambda star for which this happens. Okay, these are important conditions. So this is, it necessarily happens, right? This necessarily happens, so we call it necessary conditions. So this is there in the lecture also, right? So what is perhaps a question that we have not asked, I would say, is what about an inactive constraint? So this is important to understand. So let's go back to this image. Okay, let's copy it here, and stare at this for a moment. So now, let's say this is x comma y. Okay, you are sitting inside the constraint. Now, what are the feasible directions here?
Anywhere around this point.
Exactly. So every direction is feasible, right? So you can move anywhere, right? So you can move here. You can can move here. You can move here, 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 here. Doesn't matter where you move, right? So all directions are feasible. So what happens then? Whatever we discussed here was actually, to be very specific, it was only for the boundary part. Okay, so if it is on the boundary, then this analysis visual thing holds. But if it's inside, what can we say? Okay, so that's what we are going to look at. We can say the same thing, but this will become clear, right? So if x star, so remember that what is it that we are interested in? If x star is a local minimum, that's what we are interested in always. So if x star is a local minimum and g of x star, so is strictly less than 0, okay, meaning inactive constraint. So the constraint is inactive. You are strictly inside the region, constraint region. Then what can you say? Do you see what is it? What happens to gradient of f of x star? What do you think will happen to it?
Is equal to lambda times del G for any lambda.
That is not something you can say, because you can't say that, but think about what is happening to, see, this is a minimum, right? So see, x star is at x star, there is a minimum that is given to you. So the function is kind of having a low point here, but then that point is sitting inside the constraint. So for a very small region around the constraint, I'll draw a very, very small region surrounding the constraint, okay, around the minimum, right? So if you look at this, what can you really say? If x star is a local minimum and I am like sitting well inside the constraint, if the function is differentiable, what do you think del f of x star will be?
Increases.
0.
0, right? So that's exactly what will happen. Okay, so visualize this. For example, think of a bowl, okay, which is like what f of x comma y is x square plus y square is a bowl, okay. Now, what is the constraint? The constraint, let's say the constraint is a circle, okay. Let's say the constraint is a circle. Now, so circle is like x square plus, maybe it's circle like this, right? So x minus 3 whole square plus y minus 3 whole square minus 1, okay. So this is the constraint. Now, function is like a bowl, but the bowls, where is the, if the function were unconstrained, where is the minimum of f of x square plus y? So f of x comma y equal to x square plus y square, if the function is unconstrained.
3, 3.
No, this is function, right? So I'm minimizing f of x comma y, but it's unconstrained. Where will the minimum be? 0, 0, right? Now, if the function is constrained, but the constraint is g of x comma y less than or equal to 0, it's this circle, okay? Now, you'll have to do certain things, right? But for a moment, think of what will happen if the circle became this. Okay, the function is still constrained, But what is happening to the minimum of f? It is sitting inside the. It is already sitting inside the
Origin.
constraint, right? So it's that is the image you should have here, right? So if x star is a local minimum and that x star happens to sit directly inside g of x less than or equal to 0, that region, then you can kind of see, okay, very loosely, that the gradient is 0. Okay, so then what can you do? You are once again going back to this constraint. Okay, but here you realize that what will your, so this has to be lambda star. So what do you realize? This is already 0 in this case. So to make this still true, what should be 0?
Lambda star.
Lambda star has to be 0, right? In this case. Okay, so if the constraint is inactive, then lambda star is 0. Okay, so what have we understood? We have kind of understood the following. If the constraint, there are two things that we have seen, right? So if the constraint is active, then what have we understood? We have understood that this holds. If the constraint is inactive, meaning it is strictly inside, then also this holds actually. Okay, see, then also I can say lambda star greater than or equal to 0, but I can say something extra. What can I say? I can say that g of x star comma y star, or rather, sorry, g of x star strictly less than 0. But if I multiply lambda star and g of x star, what do I get?
0.
0, right? So I will put it this way, right? So I'll call this to be 0, and I will call this greater than or equal to 0, right? So in fact, this is like the second conclusion. So let me not confuse too much. So I'll just say that we observe that now putting these two together, in general, if x star is an optimal, so if it is a minimum, then what do we observe? We observe that this gradient is 0, lambda star is greater than or equal to 0, and since this is a minimum, the constraint has to be satisfied. So g of x star is less than or equal to 0, and lambda star into g of x star is equal to 0. Okay, so this you have to understand as follows. Now, if it is active, if the constraint is active, what is g of x star? If the constraint is active, what can you say about g of x star?
Equal to 0.
Equal to 0, right? If the constraint is inactive, then g of x star is strictly less than 0. But we just saw that you can set lambda star equal to 0. Okay, so you can set lambda star equal to 0. That will always work, right? So see, del f is 0. Okay, so for this equation to be valid, still valid, you can set lambda star equal to 0. And the first equation that we saw in the previous case will still be valid. Okay, so in addition, so this is like, I'll just add this here. This is a special case of inactive constraint. So this is less than 0, lambda star equal to 0, and this is still 0. So in the previous active case, this is g of x star is equal to 0 because it's active, it's sitting on the boundary, and this we already saw. Okay, so this is active case, this is inactive case. In general, so this, I'll remove this, okay, because I'm sorry, I've moved back and forth. I hope you have understood. So this I can remove and present this. Okay, so these conditions are called these four conditions are called the Karush-Kuhn-Tucker conditions, right? So Karush, Kuhn, and Tucker, right? So conditions. So these are necessary conditions for optimality in an unconstrained optimization problem. Okay, we have not done it rigorously, but did everyone get what we did just now? It was slightly different from what we had in the lectures. We brought in this inactive and active part, but did you get the basic idea what is happening? Any questions regarding what we just saw? Okay, right. So this, it's actually an interesting history. So this was actually discovered 2 times independently. So Kuhn and Tucker discovered it a bit later. So once they published it later on, it was known that Professor Karush had actually done it. So he had not published it. It was in his master's thesis. It was in an unpublished form. So it was originally called the Kuhn-Tucker conditions, but once the contribution of Karush came into view, they later called it Karush-Kuhn-Tucker. Okay, so these folks are closely tied to this field of game theory, economics, and all that, right? So those who have you all heard about this Nash equilibrium, John Nash, and all that?
Yeah, Beautiful Mind movie, right?
Right,
The guy.
right, that guy. So these people are like,
But most importantly, he's the father of game theory, I guess.
right, yeah. So these 3 researchers also, I believe, are closely tied to game theory and economics and all that, right? So yeah, so this is brief motivation for KKT condition. So can I move on? Shall we do one more section before closing today, or I am fine with it, but shall we do the Lagrangian also?
Yes, sir.
Okay, so we can do the Lagrangian also.
Yes, sir, please proceed.
Okay, so what is this? In the lectures, we call this each of these 4 conditions, they have a name. So this is called the Lagrangian stationarity of the Lagrangian. This is called primal feasibility. This is dual feasibility, and this is complementary slackness. Okay, so what we are going to do next is understand why these names are given. Okay, so that's what we are going to do. So for that, we have to revisit this Lagrangian, which we saw in the equality constraint. So, yeah, yes, question, Shawan. You have a question?
Sir, actually, I read some KKT thing from the books you mentioned in lectures. So numerical optimization. There I learned that KKT is constraint optimization used for constraint when there is inequality constraint where we cannot use Lagrange.
Right, you are right. So see, the KKT conditions are.
But
Oh, sorry, I said unconstrained. Is it? Sorry, yeah.
but here we learn for unconstrained.
No, sorry.
Okay,
Yeah,
okay.
I made a mistake. Yeah, so this is like, yeah, the KKT conditions are a generalization of the theory of Lagrange multipliers for constrained optimization problems with inequality constraints, right? So, yeah.
Yes, sir.
Yeah. So the lambda here is called a KKT multiplier instead of just a Lagrange multiplier, right? So if there are only equality constraints,
Yes.
this will collapse to Lagrange. Okay. So in fact,
Yes,
you can see that, right? So if
Thank you,
this inequality becomes equality, you can use this. This is still only this is the Lagrange multiplier method, right? So okay, so the Lagrangian and the primal. So we'll start understanding what we mean by this. So the Lagrangian we have already seen of a function. So the function with the optimization problem, we just look at minimize f of x. So x is here in Rd, okay, Rn. So let x be in Rn. So I'm no longer using f of x comma y. That's cumbersome. So I'm just going to say x is in Rn. Okay. Now x in Rn be the optimization variable. Okay. So you are trying to minimize f of x. We'll first look at only one inequality constraint of this form, g of x comma y less than or equal to 0. So the Lagrangian of this problem is defined as the function L of x comma lambda, and is given by L of x comma lambda is f of x plus lambda g of x. Okay, so that's the Lagrangian. So now, yeah, so this is like the constraint region, right? So let's call this where the boundary is also part of it, but that's not important. So what we are interested in is a point that is inside the Lagrangian, inside the constraint. What will be the value of L of x comma lambda, and what will be the value of this outside this constraint region? Okay, so now I'll come back to this diagram. So now we define the following function. So what we do is we say I'm going to maximize over lambda this Lagrangian. So I'll write it out this way and call this some other function, right? So maybe what is it called in the lecture? J of x, is it? Is this called J of x? I don't know what this is called in the lecture, but in fact, this is, let me not call it anything now, but let's just study what happens to this in two situations. So when the constraint is satisfied, what will happen to this? This will collapse to so if like you are subtracting, so this is negative, right? This is negative or zero. If it is zero, then first of all, if it's zero, what happens? If g of x is equal to zero, then this maximum over this becomes just
F of x.
f of x. Now, if it is less than zero, what happens? You are doing something like this, right? So you are doing f of x plus lambda into some negative number, right? So let's, for example, g of x at that point is minus 10. So what would you, if you want to maximize this quantity, when g of x is negative, what will you set lambda to?
Zero.
Zero, right? So you have control over lambda. Remember that you have control over lambda. So if you want the maximum value of this expression, so let me first write this down. So this is f of x whenever the constraint is satisfied, and if the constraint is not satisfied, then this is some positive quantity, right? So I can set this as big as I want. So this becomes infinity, right? So this Lagrangian, if you have a point, this is not the Lagrangian, but remember that this is like a new function. Okay, so if you evaluate this new function inside the constraint or on the constraint, then the value it's going to take is f of x. Okay, now the value it's going to take outside is, what is it?
Infinity.
Infinity, right? So
Infinity.
that is the diagram. This is the picture you have to keep in mind. I don't know what prof calls this, but yeah, this is anyway. This is some kind of a new function, and we are evaluating the function on all the points. Anywhere you evaluate inside, if you move this, if you keep this together, right, wherever you move, it will be the corresponding function's value at that point. Just if you step outside of this region, then it will go to infinity, right? So now, what have we done? We have reformulated formulated the objective function in a slightly different manner. Okay, that includes the constraint implicitly, right? So meaning you are not explicitly saying g of x less than or equal to 0, but kind of pulling it inside the objective itself and representing it as this form. So therefore, you can say that minimum of f of x subject to g of x less than or equal to 0. Okay, this whole thing is the same as, so this is like, how do you say equal? Okay, this is equivalent to minimize over x, maximize over lambda greater than or equal to 0, the Lagrangian. Okay, so the Lagrangian, I'm just, instead of writing it as a Lagrangian, I'll just write it explicitly. Okay, because see, whenever g of x is less than or equal to 0, this whole thing will become f of x.
Yes.
Okay, and you are minimizing over x, f of x, but then this will become f of x only when g of x less than or equal to 0. Okay, so you're essentially what you're doing, you're only searching in that region where g of x is less than or equal to 0. Okay, so is this clear? So,
Sir, can you repeat this thing again? Like what we are doing here? Like minimum over x, minimum of x, I understand, but
yeah,
what
so
will happen when gx is less than?
so you can look at, so see, we can look at this as a two-step process. Okay, what do I mean by that? First, fix x. Okay, now fix x, then whatever is inside becomes one function. Correct? So it becomes one function. It becomes a function of some function of x. Now, so it's a two-step. You can think of this as a two-step optimization problem. If x is inside the constraint, or if x satisfies the constraint, okay, g of x less than or equal to 0, then the inner optimization problem, what is the inner optimization problem? Max lambda
Max
greater than or equal to 0, this one, right? What does this become? Returns the value
f of x.
f of x. Okay, fix x. If x satisfies g of x less than or equal to 0, then it returns f of x itself. So good enough. If x doesn't, otherwise, right? Otherwise means what? If x doesn't satisfy, then the inner optimization problem returns infinity, right? So this is for one x, right? Or think about, repeat this process for all possible x. Okay, you'll get some finite values, some infinite values. I'm very crude example. It's not exactly what this happens. Say for x equal to 1, you can form a table. You can't tabulate this, but so you have to be careful with what I say. Let's say this is x, and this is the value of this whole process, right? So let us say for one value of x equal to 1, the inner problem gives you infinity. Okay, maybe for x equal to 3, it gives you, say, something else, say 1.3. Okay, and you keep doing this for 5. Once again, it gives you infinity, and for 7, it gives you some other finite value. What you need to do is you have to do minimum of all the minimum of this column. Okay, that's what you're doing. So see, every time you set an x, you get some value here that, if it is infinity, then anyway that's not, you don't care about it when it comes to minimizing it, right? So all the entries which are infinity correspond to the constraint not being satisfied, so they anyway go out, because you are only interested in minimization. Only if the constraint is satisfied will these things start mattering, right? So therefore, you are essentially solving the original problem itself. Is this clear now? Somewhat?
Yes, sir.
Okay, so what you are doing is you are just reformulating the problem. It's a min-max. This is called a min-max problem. Okay, so takes the form of minimize over something, maximize over something. If you look at it as a two-step process, it will be clearer. So now this problem is called the primal problem. So this, we call this the primal problem. Now, is the primal problem clear what we have done? Okay, so you could either call this, so I'll just call this min f of x subject to g of x less than or equal to 0 is called the primal problem. The min-max version of the primal problem is what? Min lambda greater than or equal to 0, min over x alone, right? Not min over x, lambda greater than or equal to 0, f of x plus lambda g of x. Okay, this is just another version of the same problem. This is also the primal problem. So we have not yet discussed what is called the dual. And yeah, so this is what? This is also equal to what? I can replace this with what function?
L of x.
L of x comma lambda, right? So Lagrangian. So main point to note is the following: that when the constraint is satisfied, okay, my final takeaway, the constraint is satisfied, max over lambda greater than or equal to 0, the question mark is coming here. F of x plus lambda g of x is equal to what?
F of x.
F of x, okay. So this is what is called the primal objective. So the primal objective is f of x, okay, because that's what this is, right? This is the objective. So, but often it is also written in this equivalent form, max over lambda lambda greater than or equal to 0 f of x plus lambda g of x whenever the constraint is satisfied. Okay, so you can also it is not incorrect to call this the primal objective. They are the same. F of x is, and this is same, provided lambda g of x less than or equal to 0. The constraint is satisfied. Okay, so is this clear so far? Roughly what the primal is to all of you?
Yes, sir.
Okay. Okay, so now the dual, there isn't too much motivation here, but what we typically do is we take this problem, which we call this the min-max problem, right? So we recall that the primal is this primal problem is specified as follows. And then just out of curiosity, we ask, okay, this is something we always do. Whenever you have two operations, one after the other, there is this tendency to ask what happens if you swap the operations. We ask what happens if we swap the min and max. Okay, so we get a different optimization problem, not the same. So we get max lambda greater than or equal to 0, min over x, f of x, okay, plus lambda g of x. So this we call the dual problem. So the resulting optimization problem is called the dual. So the dual is interesting because it is interesting for two main reasons. It is interesting for two main reasons. The first is the inner optimization problem. It's a min-max problem. So it's a max-min rather. Max-min problem. The inner optimization problem is what? What is special about it? It's unconstrained, right? And that's a big advantage. So you can bring all your calculus knowledge here. Gradient of this quantity is 0 at, so all that you can do, right? And the outer optimization problem is, what is special about that?
It's 10 o'clock.
Has very simple inequality constraints. So they are just bounds on lambda. You just want lambda to be non-negative, that's all. So this is a very big advantage, right? So the dual is therefore, what can you say? Has a simpler form. Okay, at least if you look at it abstractly without plugging in the values of the functions, it is simpler because you know how to solve this. And if your constraints, inequality constraints are just something greater than or equal to 0, it's much simpler, right? Imagine having something like x square plus y square less than or equal to 1, right? That's a circle. So, but here it's just sine of lambda. Okay, so that is what is called the dual. The dual objective function, right? So just like the primal has an objective, the dual also has an objective. It's given by, what is the dual objective given by? This quantity. So whatever you see there, that is what is the dual objective. So it's a function of lambda. Why do you think it's a function of lambda? Why not a function of x? Can someone tell me why it is not a function of x and it's a function of lambda only?
Because we are minimizing over x and maximizing over lambda after we minimize over x.
Correct, yeah. So your x goes out of the picture here. Since you have minimized over x, this is the only variable here is lambda. Right? So for example, when you minimize, it could turn out that x equal to 7 is where this minimum occurs. So it will become f of 7 plus lambda g of 7. So d of lambda finally will end up to be some function of lambda. Okay, so this is the dual objective. Now, yeah, so do you want, I can go on for 5 more minutes and talk about this duality gap, okay, or the dual gap, or we can stop here and start from dual gap next on Saturday. So which one do you want? Do you want me to discuss dual gap now, or can do both ways?
I think we are in a flow. It's better to continue, sir. Like that's what my opinion.
Okay. Yeah, so I can do the dual gap now, and maybe from convex optimization we can resume on Saturday. So what is this dual gap? That's what we have to understand. So let's first look at d of lambda. Okay, it's a slightly tricky concept, so let's go a bit slowly. So this is minimum of x, f of x plus lambda g of x. Okay, so first of all, what are we trying to understand? What are we trying to study? So there are now two optimization problems. Okay, so one is called the primal, another one is called the dual. So the primal is a function of, so the optimization variable is x. Okay, here the optimization variable is lambda. So the question is, how are these two problems related? Okay, by shifting the max and min, by swapping them, we came to the dual. So the question is, are they related or not? If they are related, what is the relationship? That's what we are asking. Okay, so this is the question that we are trying to answer. How are the two problems related? So this is what we call the dual objective, right? Min over x, f of x plus lambda g of x. Now, notice that since you are minimizing, okay, this is for any lambda, right? What will happen? The minimum will always be less than or equal to f of x plus lambda g of x. Do you agree? This step. Do you agree? This is what we have done here. Is it clear to everyone that the minimum of this function will always be less than or equal to f of x plus lambda g of x?
Yes, sir.
Okay, so this is true for any lambda on the left hand side, okay, and any x. Okay, what is true? This inequality. So this is where things will start getting slightly tricky. So what am I saying? The following inequality is true for any lambda greater than or equal to 0. It's in fact for any lambda, not necessarily, but then it's okay. And for any x. Okay, this is the following inequality. So now, since this is true for any x, now consider those values of x where g of x less than or equal to 0. The constraint, the primal constraint. This is called the primal constraint. So you have a optimization variable is x. There is a what we call a primal objective. So the objective that is f of x. Okay, remember. And there is a primal constraint. What is the primal constraint? G of x is
Less than equal to
0. Correct. Correct. Right. So that is likewise for the dual. You have a dual objective. You have a dual. You have a dual objective, which is what we have been calling d of lambda. And there is a dual constraint. What is the dual constraint?
lambda greater than equal to 0.
Lambda greater than or equal to 0. Okay, so these are the two problems and their corresponding. So you have already set the dual objective. You have said that, sorry, dual constraint. Now we constrain for x. So since this is true for any x, it should also be true for x where g of x less than or equal to 0. Okay. So this inequality, above inequality, is still true for any lambda greater than or equal to 0. Sorry, and any x that satisfies g of x less than or equal to 0. Okay. Therefore, this is there. But then since g of x is less than or equal to 0, what are you doing to f of x? You are subtracting something from f of x. Therefore, this is going to be less than or equal to what? You are subtracting a positive quantity from f of x. Therefore, this will be less than or equal to f of x. Right? Do you see that? So this is like 10 and this is like minus 3. So this will be less than or equal to 10. So what we have shown is that whenever lambda is greater than or equal to 0 and x satisfies g of x less than or equal to 0. Sorry, this 9 is coming because it's the, yeah. This is like primal and dual feasibility are met. Then what we can say is the primal objective is always less than or equal to the dual. Sorry, the dual objective is always less than or equal to the primal objective. Okay, so this is a very important result. So when the primal, the dual objective is always less than or equal to the primal objective for any pair of points x and lambda that satisfy the dual and primal feasibility conditions. Okay, so this is the relationship that we are trying to go towards. How are these two problems related? What we see is that the primal is always an upper bound for the dual, or alternatively the dual is a lower bound for the primal. So that particularly if lambda star, okay, so lambda star is what is the dual optimal, okay, so and x star is the primal optimal, then this holds, right? This still holds. D of lambda star is still less than or equal to f of x star. Okay, the gap between them. What is the gap? The absolute value, or f of x star minus d of lambda star, is called the duality gap. So there's a gap, meaning there is some distance between the optimal solution's value here and the optimal solution's value there. Okay. So if the duality gap is 0, meaning if f of x star is equal to d of lambda star, then we say that strong duality holds. Okay. So this is what you have to understand for this primal and dual problems. So there is something known as duality gap, or dual gap, which says that there is a distance between the dual objective value and the primal objective's value. The primal is always bigger than the dual, and at the optimum values, which is lambda star and x star, whatever is the distance between them, that's called the duality gap. If it is 0, that means we say that strong duality holds. Okay, so we will soon see that if the function is convex, if objective function and the constraints are convex, the objective functions and the constraints are convex with some other conditions, then strong duality holds, and this will lead to some very good solutions to the problem, right? The KKT solution, the KKT conditions mainly, we will revisit them, but mainly you want to understand this part, right? Strong duality holds. So what does that mean? If strong duality holds, what is the big advantage? Can someone tell me what is the advantage of having f of x star equal to d of lambda star?
Then we can solve the dual problem instead of primal, which
Exactly.
is easier.
So exactly. So this means that we can solve the simpler dual problem instead of the primal, right? The solution is the same as we just saw. The final value of the objective is the same. So, and all these, the advantage of having a nice form for the dual will come to a rescue. So you can solve the dual and say that I have solved the problem. But then for that, your functions have to be convex, which is why we spent so much time on convex functions. Okay. Yeah. So that is. Let's stop here because the next is like convex optimization. What is a convex optimization problem? What are the KKT conditions? So KKT we have already seen, but we'll see with some examples also. Yeah. Yes. Yeah. Sure. Question.
Sir,
Sorry.
sorry, I was muted. The when will you upload the previous 2 weeks note, week 8 and week 9.
Week 8 is not uploaded, is it? So week 9 I have to complete it. Week 10 I'll maybe upload soon.
No, not week 10. Week 8. Your notes are not there in portal.
Yeah, week 8 I didn't take the session, so I don't have notes for week 8.
Okay.
Week 9 I
Okay.
meant to upload, so I'll finish week 9 and upload soon.
Okay. This is the note only. After week 10, you can upload it.
Yeah. I'll upload week 9 and 10 together.
Okay. No problem. Thank you.
Okay. Any other questions that you have regarding the primal dual?
It is a bit complicated currently.
Correct.
I will read the notes.
Yeah, so it is hard. So it is very hard. So I understand it is this dual
Lagrangian multiplier and that thing KKT. What you taught, that is not so much hard actually, but this portion I found it's
yeah. So the
little
dual
complicated actually.
Correct. Yeah. What you can do is there is one professor today only I discovered. His name is what was his name? He's from Georgia Tech. So Georgia Tech. Wait a minute. So there are Georgia Tech. Of name is Davenport. Okay, Davenport. Mark A. Davenport. So this is the prof. So he has a set of notes for optimization. It says optimization for information systems, but you can go there. There is this is very, very nicely done. So Karush-Kunteker conditions he has beautifully explained for this is what I'll also be covering. So this SVM part you can skip, but everything that comes before the SVM, Lagrangian duality. So he follows the same notation as our prof. So that is also good. What is the dual problem? And I have used his notation only. In fact, I have used many things from him directly.
Sir, can you send the link?
Yeah. So this is from yes. Yeah, this is the page. Optimization for information systems, but then it's optimization is everywhere, so kind of doesn't matter whether it's for information systems or machine learning. It's all one and the same. Okay, so we'll meet again on Saturday then. Is that fine? 4 to 6.
Yes, sir.
Yeah. Thank you, sir.
Okay then.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.